Hello everyone. So far in this course, we have looked into seismic design and ductile detailing of new buildings, whether it is reinforced concrete, steel or masonry building, and their architectural elements and utilities. Today, we will start our journey into seismic protection of existing buildings. This is very important given that a lot of our infrastructure, including buildings, is aging, and it is important to save them from wrath of future earthquakes. So, in this class, we will start with discussion of the process related to seismic evaluation and protection of existing buildings. Then we will make our way particularly into reinforced concrete buildings, because they are the most common building forms in our country, where we will look into preliminary evaluation process in greater depth in today's class. So, when it comes to seismic evaluation of a building, there are different approaches. The approaches may be classified into two major categories, the first being qualitative method and the second being analytical method. In the qualitative method, we have a few components such as visual inspection. We go to the site and look how the building looks from the structural engineering perspective. We do the condition assessment, in which we record every sign of distress, structural and non-structural. Then we do some non-destructive testing. Without destroying the structure, we will test and determine what is the current scenario of the building as well as the material used in the building. Then the other class of method is called analytical method, in which we perform some numerical modeling and analysis. The method can be equivalent to static or dynamic analysis method. We can go for pushover analysis, response spectrum method, time history analysis method, and so on. I hope you are familiar with all these methods, as we have discussed them over first few weeks of this course. Then, based on these methods, when we conduct the numerical modeling and analysis, from there we can obtain what is the capacity of the structure and what is the seismic demand on the building. So, based on the capacity of the building and the demand on the building, we will be able to draw capacity demand spectra and judge whether the building is safe against future earthquakes or not, or how safe it is against any future earthquake. And upon evaluation, if we find that we need to have some structural intervention in the building to make it safer against future earthquakes, then within the structural intervention we can have different forms of interventions. The simplest being repair or restoration. Then we can move to strengthening and further to retrofitting. Now let us look what is the difference between these terms, which people commonly use without understanding the exact difference between them. So, structural repair or restoration is a process in which the original strength of the building is restored. The building has suffered material and structural degradation over time, and we end up restoring the original strength of the building. So, that process is called repair or restoration. Now, if we upgrade seismic resistance of the damaged building so as to make it safer against future earthquake, then such a process will be called as seismic strengthening. So, for seismic strengthening, we are taking a step further. We are not only restoring the original strength, we are imbibing a higher seismic resistance so that the building will be safe against future earthquakes. In case of retrofitting, we will take one more step further, that we will upgrade it to the level of the present day codes using appropriate techniques. In this case, at this point I would like to reiterate that as we go to more recent versions of codes, you will find that the previous structures would be found deficient, and then if we are upgrading their seismic resistance to the level of the present day codes, it means that we shall be improving their seismic resistance. Okay, once we have understood the difference between repair or restoration, strengthening and retrofitting, now let us look into various types of retrofitting. Majorly, the retrofitting approach can be classified into two broad categories: global retrofitting and local retrofitting. Global retrofitting is also called as structure level retrofitting, and the local retrofitting is also called as member level retrofitting. The structural level or global retrofitting is employed when many structural members are found to be deficient as per the present day codes. In this case, we modify the behavior of lateral load resisting system of the building in order to be safe as per the present day code. So, what can be the example of such a retrofitting strategy? If we add a shear wall or a structural braces to some of the frame beige, then in that case we are increasing the stiffness of the building. If we increase the stiffness of the building, the dynamics of the building will change, and therefore we are actually modifying the behavior of the lateral load resisting system of the building. We can add new load parts. This is usually done when you have very few load parts. So, to add redundancy into the structure or to add new load parts, we will do some modification to the structural form. It may be the addition of shear wall or structural braces and so on. Sometimes we find that there can be a very heavy mass which is leading to mass eccentricity in the building, whether in plan or in elevation. In these cases, we do the redistribution or reduction of mass. Then installation of base isolation systems and supplemental damping devices, these are also affecting the behavior of the lateral load resisting system, and therefore they will be classified as global retrofitting or a structural level retrofitting. We will look more about these base isolation and supplemental damping devices as we go towards the end of this course. Then in the member level or local retrofitting, such retrofitting is employed when very few structural members are deficient. So, we will apply retrofitting to only those structural members which are deficient. So, it will strengthen certain structural members to achieve desired limit states. There can be multiple examples such as jacketing of structural members, beams, columns, shear walls and joints. We will learn about jacketing as we go further. Then grouting of cracked structural members and strengthening of individual footings. All these are member level or local retrofitting measures. Now, once we have understood what are the different types of retrofitting, now let us get into seismic protection of reinforced concrete building in particular, because reinforced concrete buildings are the majority of engineered structures in our country. So, the first thing which we will look over here is the process of evaluating any existing RC building. In this case, what shall be the criteria for our evaluation? So, our criteria will be based on how do you calculate the capacity or how do you calculate the demand. So, for demand, we shall use appropriately modified design seismic force based on the latest version of IS 1893 part 1. Currently, the latest version is 2016. So, we will use seismic zone, building type, response reaction factor directly from this code, and based on this we shall be able to obtain the design seismic force, but then we will also apply some modifications to this design seismic force. Remember, we are actually calculating the demand. So, we will modify this demand based on some factor. What shall be that factor? What is the usable life remaining? Since IS 1893 part 1 2016 gives you the design seismic force for constructing a new building, let us say that the design life is 50 years, but the building has already been in service for 40 years. So, we do not expect this 40-year-old building to achieve a performance for a design life of 50 more years. We do not want that. So, for us the remaining service life is only 10 years. So, we can have some discounted design seismic force. So, these are the modifications that we apply over here. Then as we go to further newer revisions of IS 1893, that is from 1962 to 66 to 75 to 84 to 2002 and further to 2016, we will find that the buildings designed as per the previous code will be found deficient to some extent. But in this case, the retrofitting decision will be based on the discretion of engineer in charge. It does not mean that the building is now unsafe, because it was perceived to be safe as per the code which was existing at the time of the building construction. So, it is deficient as per the current day code. And for simpler buildings, let us say buildings which are designed as per IS 1893 and not on stilts, which means that the ground floor is not open ground story and the column dimensions are more than 230 millimeters, then in that case there is no need to retrofit such a structure. Again, let me reiterate that retrofitting means to upgrading seismic resistance of a building to the level of present day code. It does not mean seismic strengthening, which implies just to upgrade the seismic resistance. So, buildings which are designed as per any previous version of IS 1893 and not on stilts and have column dimensions more than 230 millimeters, based on the current condition, they may need some seismic strengthening, but they do not need seismic retrofitting, which means you do not have to bring their seismic resistance to the level of present day code. So, these are based on section 5 of IS 15988 2013. So, I suggest you to have a copy of this code ready at your desk, so that you can look into this code, which is about seismic evaluation and retrofitting of reinforced concrete building. Now, once we are having the understanding of evaluation criteria, let us look into what are the different modifications that we were talking some time back. So, the first modification factor is about the lateral load modification factor, which depends on remaining useful life of the building. So, this very value u is given by square root of the ratio of the remaining useful life of building to the design life of the building. Suppose the building was designed for 50 years, it has been in service for 40 years, then the T remaining shall be equal to 10 and T design shall be equal to 50, and this value cannot be taken to be less than 0.7, it has to be more than or equal to 0.7. For critical buildings which need to be operational in the aftermath of an earthquake, for such buildings u may be taken as equal to 1. Now, where will you use the value of u? You will multiply the design lateral force by u. So, the design lateral force for a building, so the design lateral force for an existing building will be u times the design lateral force for a new building. Similarly, for an existing building, the measured or probable nominal strength of material, which is obtained either through field or lab tests or using relevant clauses in IS 15988 2013, this probable or measured nominal strength will be multiplied with knowledge factor, which is again given in table 1 of the code IS 15988. Now, what is knowledge factor? Knowledge factor is a factor that takes care of the reliability of the information that you are having about the existing building. You do not know every detail of your existing building, that is why the knowledge factor will be usually less than 1, but if you have all the details, it will be equal to 1. Let us look into some examples. For example, if you have original construction documents available with you including post-construction activities such as modification to a structure or material testing undertaken of existing structure. In such cases, you can use the knowledge factor of 1. You can tell that I know with certainty that this is going to be the probable or measured nominal strength of the material. But let us say that the documentation is incomplete or there is no document available, but you conduct extensive testing and inspection to establish current strength of load resisting members. How do you do this? You inspect the building, you record all the structural distances and you do extensive testing. We will discuss more about this as we proceed to the next class. Then in this case, the knowledge factor shall be equal to 0.7, which means that we are saying that our probable strength of the material is only 70% of the probable strength of the material because of the lack of information. Okay. Once we have looked into seismic evaluation criteria, now let us look into the process. How do we perform the seismic evaluation? Particularly, there are two stages in a seismic evaluation project. The first stage is preliminary evaluation and the second stage is a detailed evaluation. The first stage, that is the preliminary evaluation, acts as a screener for detailed evaluation. It tells you whether you need to conduct the detailed evaluation or not. So, it involves broad assessment of physical condition, robustness, structural integrity and the strength of structure, including simple calculations. We will look some more detail as we proceed through today's lecture, and it is a quick procedure to establish actual structural layout and assess its characteristics that may affect seismic vulnerability of the building. Now, based on this quick assessment, we will observe whether our building satisfies some checks or not, and if those checks are satisfied with acceptable results. What are those checks? Those checks are related to strength, overall stability and integrity, and if these are found to be acceptable, then we will tell that we do not need any detailed evaluation. Further, for a very small building, let us say a building which has storage up to 2, the floor area is less than 300 square meter and the building is not being used for a critical purpose such as hospitals which are needed in the post earthquake emergency response phase. So, in this case, you can directly tell that you do not need any detailed evaluation even if you observe some deficiencies. So, basically you note down the deficiency and you perform strengthening, but you do not do the detailed evaluation. Now, if your building fails to give you acceptable results related to strength, overall stability and integrity, or there are some more conditions when you need to perform detailed evaluation. We will look about those conditions as well in some time, and in the detailed evaluation we will perform numerical checks on stability and integrity of whole structure as well as the strength of each member. Now, in this case we shall use modified demands and strengths. Now, let us quickly summarize these two phases of the seismic evaluation process before we go into detail of preliminary evaluation. So, the first step is to conduct a preliminary evaluation of the building, which is meant to understand overall seismic vulnerability or to assess overall seismic vulnerability of the building, and based on these results we shall try to satisfy the criteria related to strength, stability and integrity, and if those criteria are satisfied, then we will directly conclude that there is no retrofit required for the given building. If those criteria are not satisfied, then we shall go for detailed evaluation. The detailed evaluation is for primary lateral load resisting system, and after conducting the detailed evaluation we will again check some criteria, and if those criteria are satisfied, then we will conclude that we do not need any retrofit. But if those criteria are not satisfied, then we shall recommend suitable retrofit measures for the building. I have provided the section and clauses related to preliminary and detailed evaluation as well as the acceptability criteria related to either step. So, the acceptability criteria is different for different phases, that it is different for preliminary evaluation and detailed evaluation. They are given in clause 6.6 and clause 7.3 respectively of IS 15988. Now, once we have understood that a typical seismic evaluation process comprises of two phases, one is preliminary evaluation and the second is detailed evaluation, we will try to understand more about preliminary evaluation now. So, in preliminary evaluation, let us look into the procedure first. The first step which we will do is to visit the site and collect the data. In this case, if we have some data available with us in form of some documents prior to visiting the site, we will do the study and then we will verify those details in the site. Apart from verifying those details, sometimes you may not have the detail at the start, then our goal will be to collect additional building data. And during the visit, we shall also determine the condition of the building and its components apart from noting down these building data. So, by determining the condition of the building and its components, we mean that we shall look for different type of distress and what are the implications or what do we infer from those structural distress signs. So, after visiting the site and collecting the data, we shall go for acceptable criteria. We shall go for different checks related to configuration and strength. So, the configuration related checks shall be related to load path, geometry, weak or soft story, vertical discontinuities, mass irregularity, torsion, adjacent building, short columns. So, majorly about the different plan and elevation irregularities which we have looked into while we were looking into key elements of good seismic design in the first week itself. So, those things we will check. Then we have a strength related check. In the strength related check, we will determine the modified demand lateral force considering occupancy risk factor and usable life factor. We shall check shear stress and axial stress in different components of the building. We will see these in more detail now, and based on these acceptable criteria, whether they are satisfied or not, we shall recommend detailed evaluation, whether we should conduct the detailed evaluation or not. So, now let us look into the first step, which was about site visit and collection of data. What are the different types of data that we want to confirm or collect during our site visit? So, the first thing is the general information related to building. We shall collect data related to what are the number of stories in the building, what are the dimensions of the building in plan and in elevation, and when was the building constructed, so that we shall be able to understand what is the usable duration or usable service life remaining for the building. Here we shall also collect data related to a structural system description. In this, there are multiple things. First of all, we will try to find out, is the building built as one single unit or there are multiple units separated by construction joints. And then we shall also note down the vertical lateral force resisting system, their location and other details, that is columns and shear walls. Then we shall also understand the nature of floor and roof diaphragm, whether they are providing us the rigid diaphragm action or flexible diaphragm action. We will also look into the details related to basement and foundation system. Apart from the structural system description, we shall look into building type and site soil classification, particularly from the context of IS 1893 Part 1 2016. Why is it important? Because from here only we shall be able to calculate the design seismic load or the demand on the building, and then we have to modify that demand accordingly. The building use shall be recorded. What is the nature of occupancy? Are there any adjacent buildings? Are the buildings spaced adequately, or there is a potential for pounding and falling hazard? Then apart from this, we shall also record data related to the general condition of the building. Does the material which has been used in the building looks deteriorated and dilapidated? An example is, has the concrete of the slab spoiled? Are you able to see the reinforcement? Are they exposed? Are they corroded? And so on. Then damage from past earthquake. This shall be obtained from records which people would have made just after the earthquake, that related to various structural distress in different buildings. This may not be available in every case. Then what are the alterations that has been done in building over its previous service life that can affect seismic performance of the building? We shall also look into what are the different architectural features that are affecting seismic performance, especially location of masonry infill walls. We shall also look into geological site hazards and foundation conditions, whether the soil at the site is susceptible for liquefaction, whether the site is also susceptible to slope failure, or is there any surface fault rupture happening nearby? Is there any large fault movement in the vicinity? Are you located somewhere close to an earthquake source? All these things are very important to understand or to collect the data, which will help us in our detailed evaluation later. Then, has there been any anomaly or special construction conditions during the construction stage? So, after collecting all these data, now we shall go to various checks related to configuration and capacity. First, we will look about different configuration related checks. The first thing is load path. So, there must be at least one rational and complete load path for seismic forces in either horizontal direction, so that all the inertial forces may be transferred from the building to foundation. So, if you do not have a complete load path in any of the orthogonal direction, then in that case you will tell that the building is deficient from the load path perspective. Then redundancy in any direction, in any principal direction, whether be it x or y. I am talking about the plan directions. We should have at least two lines of vertical lateral load resisting elements. What are the vertical lateral load resisting elements? These are columns and shear walls in an RC building. So, are there two lines of these vertical lateral load resisting elements, or they are not? That you have to find it out. So, you cannot have a very thin building constructed on 5 columns placed like this, because what you are lacking is two lines of lateral load resisting elements in that case. Then the horizontal dimension of lateral load resisting system at any relative, at any story relative to adjacent story must not exceed 50% change, which means if the plan dimension at any story is L by B, you cannot have 0.4 L or 0.3 B kind of thing in the upper story. That much reduction you should not be having. If that is available, then we will say that the building is deficient. Then related to weak and soft story, if the strength of lateral load resisting system at any story is less than 70% of the strength in the adjacent story, we shall call that story to be a weak story. If the stiffness of lateral load resisting system at any story is less than 60% of the stiffness in the adjacent story or less than 70% of the average stiffness of the 3 stories above, we shall call such story to be soft story, and these are deficiencies. So, if these are available, which means that the check is not satisfied. Then we can have vertical discontinuities, that is a lateral load resisting system. There is a column which is coming from all the way from top, and then suddenly at the ground floor level you do not have that column, it is kept on a cantilever girder. So, that is kind of a vertical discontinuity. So, those things should not be there. Then mass irregularity, which is change in effective mass from one story to another, and it should not exceed 100%. So, you can have the mass of a story which is half of the adjacent story, but it should not be less than half. This is particularly important in some cases where we do not need to consider this mass irregularity, which are light roofs, penthouse and mezzanine floors, which are built mostly on the top story of the building. Then we can have torsional irregularity, that is the distance between center of mass and center of stiffness at any story must be less than 30% of the building dimension at the right angle to the direction of the seismic load considered. Then we will check for adjacent building. The clear horizontal distance between adjacent buildings should be at least 4% of the height of the shorter building. If the two adjacent buildings are having the same height and the floors are also at the same level, then in that case the minimum clear distance is given by this very expression, R1 delta 1 plus R2 delta 2, where R1 and R2 are the response reaction factors and delta 1 and delta 2 are the lateral translation in those two buildings. Now, sometimes due to presence of infill walls or parapet walls, your column becomes a short column. In that case, the reduced height must not be less than 5 times the dimension of the column in the direction of fixity, or 50% of the nominal height of typical columns in that story. If it is less than that, then you need to consider short column behavior, or you say that this very building is not satisfying the configuration related check or criteria. Okay. If you have used mezzanine or loft or subfloors, then they should be braced independently from the main structure or anchored to lateral load resisting elements of the main structure. If it is not anchored properly, then we will say that the building is failing the configuration related check. Now, once we have understood the configuration related check, now let us look into the strength related checks. So, these are quick and approximate checks for strength and stiffness of building components, and the first step is to obtain the seismic base shear and the story shear using IS 1893 part 1 2016. We shall also use IS 15988 to modify the seismic base shear for usable life remaining. Then we shall calculate the average shear stress in RC columns. This shall be calculated using this very expression, where NC is the total number of columns and NF is the total number of frames in the direction of the loading, and Vj is the story shear at level J, and AC is the total cross sectional area of columns. So, using this expression we shall obtain what is the average shear stress in the columns, and this average shear stress should not exceed 0.4 megapascal or 0.1 times of square root of FCK, whichever is lower. Further, we have RC buildings which have shear walls. So, for calculating the average shear stress in shear walls, it is further easier. It is calculated as the ratio of the story shear at that level to the total area of shear wall in the direction of the loading. So, we will consider only those shear walls for area calculation. which are in the direction of the loading, and the value of average shear stress in shear wall should not exceed these limits, which are depending on what is the kind of shear wall. For reinforced concrete shear wall, the limit is 0.4 megapascal. For unreinforced masonry shear wall, the limit is 0.1 megapascal, and for reinforced masonry shear wall, the limit is 0.3 megapascal. So, as you can see, the higher complex system we go, that is the RC shear wall, we can have a higher average shear stress, that is up to 0.4 megapascal. But if we go for a very simple building typology, that is unreinforced masonry shear wall, then in that case the limit is also very low. Now, apart from checking the average shear stress in column and walls, we shall also check the axial stress in moment frame. So, the maximum compressive stress in columns at the base due to overturning forces F0 alone is given by this very expression. Let us dissect this very expression. VB is the base shear, NF is the total number of frames in the direction of loading. So, each frame takes care of a base shear, which is VB upon NF. And if we model any building as a single degree of freedom system, the lateral force F0 shall be applied at 2/3 height of the building, and the overturning moment will be 2/3 of H. And then we have the L, which is the length of the building in the direction of the earthquake loading. Now, this very value of axial stress shall not exceed 0.25 times of FCK, where FCK is the characteristic compressive strength of concrete. Now, once we have done the checks, that is acceptability criteria, whether our configuration and strength related checks are satisfying or not, then based on these we can recommend for detailed evaluation. We can conclude whether we need to have a detailed evaluation or not. If your building satisfies the requirements or the criteria which we discussed during the preliminary evaluation stage, then we do not need to conduct a detailed evaluation. But if the building fails to comply these requirements, then we need to conduct the detailed evaluation. Further, if the building is 6 stories high or even higher, then in that case you must perform the detailed evaluation. If the building is located on incompetent, that is a liquefiable soil, then in that case you must be performing a detailed evaluation. If your building is located within 15 kilometers of active faults, then you need to conduct detailed evaluation for such building. Now, these days we have the data about the active faults available to us in form of fault atlas. Then if the building has inadequate foundation detail, then in that case we shall be doing the detailed evaluation for sure. If the building has inadequate connection between primary structural members, which is usually manifested in form of poorly designed or constructed joints in precast construction, then also we shall be doing the detailed evaluation. So, let us summarize. In this class, we have discussed about the methodology that we adopt for seismic evaluation and seismic protection of buildings, and particularly to reinforced concrete building, we have looked into seismic evaluation procedure. In the seismic evaluation procedure, we have discussed about preliminary evaluation in detail. In the next class, we will learn more about detailed evaluation of reinforced concrete building in detail. Thank you.